Hi folks, we're going to take a look at page 255, number 20, A and C. And these are very similar problems. And as I've said a couple of times already, anytime I see an expression that's a subtraction of two other expressions, I should be considering whether it can be written as a difference of squares. Because a difference of squares, as you remember, can be factored very easily. So anytime I can write something as a squared minus b squared, that factors to a plus b times a minus b. All right, so if I take a look at this first expression, well, I can see already that the term on the left is already a perfect square. Okay, and well, I recognize 16 as just being equal to 4 squared. So I've managed to rewrite this expression as a difference of squares. So now I can just go ahead and follow the factorization. Okay. Now, if you multiply this out, you can always check that it's indeed equal to a squared minus b squared, but you should be getting to the point where you just know this factorization without having to think about why it works, okay? So it's just equal to the first plus the second, so x minus 4 plus 4 times the first, whoops, sorry, that's x minus 4 plus, sorry, minus the second. So I'm going to put brackets there just to show that that's the first term. So again, remember the factorization is the first plus the second times the first minus the second. But of course, I can keep going because I see some like terms in both of these brackets, and the expectation is that you are going to simplify these. So here I have x minus 4 plus 4, so the 4's just add up to 0. Okay, so I'm just left with x from the first bracket, and in the second bracket I have x minus 4 minus another 4. That just gives me x minus 8. Okay, so quite an easy factorization, and this is a much easier, much simpler expression than the one I started off with. All right, so in this one here, neither of them are given as perfect squares, but this is where you start to recognize possibilities. So I see 25 and 9 are both themselves perfect squares, so I know that's going to work. Okay, and this is where I now need you to think. So I'm going to try to set it up as a difference of squares. So here I'm going to have 5 squared 25. Here 3 squared is going to give me 9. So I just need to see if I can write this variable component, this power, as a perfect square. And this is where I want you to think of your exponent rules, okay? Because I'm going to have the power of a power, okay? And what's the rule when I have the power of a power? I multiply the exponents. So is there a number which multiplies to 2 to give me 4? Well, yeah, 2. So here, I can just put x squared. So let's see if this works. What happens when I square 5x squared? Well, I get 25 times x squared squared is just x to the 4th. Same thing here with the y. I can just put a y squared in there. Let's check that it works. 3 squared is 9. Y squared to the power of 2. Again, I multiply the exponents. Gives me y to the 4. So I was able to write this expression as a difference of squares. And so now I can apply my factorization. It's just the first plus the second times the first minus the second. All right. Now, if I take a look at this second expression, I again see two terms that are being subtracted. Okay. Could this be another difference of squares that I can factor a second time? Well, in this case here, it turns out no, because 5 is not a perfect square and 3 is not a perfect square. Okay. So that's not the case. So just to recap, in both of these instances, we saw expressions where we had two things subtracted. So we had to ask ourselves, can we write this as a difference of squared, and then apply our easy factorization? Okay. Eventually, you'll be able to go from this step to that step without having to write this middle one. Same thing here, from the first step all the way to the final answer without having to write this middle step. For now, I would suggest that you do this every time, just so that you can recognize the difference of squares. Okay, that's it for these.